If beta and sigma square are both unknown, right? So then our job is to derive the posterior density of beta and sigma square given y, right? Okay. Okay. So this is our primary goal, and to do so, we are going to compute or calculate the posterior density of beta and sigma square given y. And we know that this is proportional to the likelihood and prior density of beta and prior density of sigma square. And also we know that this likelihood is multivariate normal density, and prior density of beta is normal density, and prior density of sigma square is inverse gamma density, right? Then the next, what do we have to do? We have to arrange this equation with respect to what? Beta and sigma square. But unfortunately, it's not possible to derive any standard density, which means you can arrange this equation with respect to beta and sigma square, but this density has been unknown. This is not standard, which means you cannot find this density in any statistics textbook. So there is no analytical solution. You cannot derive any standard density by handwriting, right? So instead we are going to rely on the numerical method, which is just computing or programming using MATLAB. Okay, the method is called Gibbs sampling. Okay, I'm going to give you just intuition and then just technical details. Instead, I'm not going to prove how or why it works, right? Okay. So here is the how we are going to do. Okay. Again, let me go back here. Okay. This is our primary goal in this posterior update, right? What do we have to know? What we want to know is the posterior mean and variance of sigma square. Okay. To do this, we are not going to derive its density. Instead, we are going to sample or draw samples from this normal distribution. Okay. How? Okay, let me give you how. Okay. So first, we know the distribution of beta given y and sigma square. Okay. And also we know the distribution of sigma square given y and beta, right? So this distribution is of course different from this and different from this, right? Okay, this is called posterior distribution. Okay, what about this? This is called full conditional distribution. Full conditional. Full means that, just take a look at here. What are the random variables? What are the random variables? Beta, y, and sigma square. All these three variables are random variables. And now later on we can observe some realizations of y though, right? So basically there are three random variables: beta, y, and sigma square. And according to this conditional distribution, this is conditional distribution of beta, and given all the other random variables. So the other random variables are fully given. That's why it's called full conditional distribution. And same for this. This is full conditional distribution of sigma square, right? Because all the other random variables are given. Given the other random variables, this is distribution of sigma square. So the other random variables are fully given, right? So that's why this is called full conditional distribution. And we know that the full conditional distribution of beta is normal, and full conditional distribution of sigma square is inverse gamma. So that once sigma square is given, then I know how to sample the beta from this normal distribution. And once beta is given, then I know how to sample or draw a sample from this inverse gamma distribution, right? And then we can repeat the sampling beta and sigma square many times. Then finally we will have many samples for beta and sigma square. And then it turns out that those samples for beta and sigma squares are actually the samples from posterior distribution. This is really amazing. Okay, let me explain this again. This is extremely difficult. This is extremely important, not difficult. This is really easy to implement, and you'll see that. Okay. Again, here is the algorithm. Okay, just specify the initial value for sigma square. Just suppose the initial value for sigma square is just post a prior mean, right? Prior mean. So suppose sigma square is given at its prior mean. So anyway, sigma square is given. Okay, sigma square given. So sigma square is given. Given sigma square, can you compute the mean and variance here? Okay, let's see how to compute mean and variance. And we know the formula for mean. So mean is here. B1 times A. Where is B1? B1 is here. Okay. To compute B1, what do you need? We need X and capital B0. Do we have X? Yes, we have X because X is just observation. Okay, the X is just data. And do we have B0? Yes, we have B0 because where is B0? You choose your own B0, right? So B0 is none. So then you can compute B1. What about A? To compute A, we need X, Y, B0, and beta 0. Do we have X and Y? Yes, of course we have X and Y. Do we have B0? Yes. Do we have beta 0? Yes. Because B0 and beta 0 are both 1. These are hyperparameters. Those parameters are chosen by yourself, right? So then we can compute B1 and A, right? So it's possible to compute mean. What about variance? To compute variance, what do you need? You need sigma square. Do we have sigma square? Yes, we have sigma square at its prior mean, and we have B1 of course. So then we can sample beta from this normal distribution and save it. Now we have beta. Okay, now you have beta. Okay, and that's denoted by beta j, whatever. Anyway, the point is that we have beta. Okay, given beta, let's see if we can sample sigma square from this inverse gamma. What do we need? We need alpha 1 and this one. Okay, where is alpha 1? Alpha 1 is what? Alpha 0 plus sample size. Do we know alpha 0? Yes, alpha 0 is what? This is also hyperparameter, and this is sample size. Yes, alpha 1 is given. What about this? What do we need? We need y and x. Of course, we have y and x. What about beta? Do we have beta? Yes, we have beta. Where is it? It's from what? It's from this normal distribution. It has been saved from this step 1, right? So we can compute this residual, and this is also residual. This is the sum of squared residual. Do we have gamma 0? Do we have delta 0? Yes, we have delta 0. Where is it? Delta 0 is also what? Hyperparameter, right? So these two steps is called one cycle or one iteration. One iteration. And then in the second iteration, we can draw beta again. Where is sigma square? Now this sigma square is from what? It's from the sample of sigma square saved from the first iteration, not this initial value. Okay, this initial value is used only once at the first iteration. From the second iteration, sigma square is from the previous iteration. Okay, and then we draw beta from this normal distribution. So over iterations, what changes? B1 and A changes? No, B1 and A do not change because right. But just look at B1 is what? B1 is determined by X and B0. Those are not change. Those are not changing over the iterations. And same for A. So B1 and A are fixed over the iterations. So posterior, so this mean the full conditional mean is fixed. What about this? Full conditional variance is not fixed. Although B1 is fixed, but sigma square changes over iterations, right? Okay. And what about full conditional distribution of sigma square? Alpha 1 is fixed, but this term changes across iterations. Why? Beta will be different, right? Beta will be different in every iteration. Okay? So we repeat these steps 1 and 2, say 10,000 times. Then we will have samples for beta and sigma square. How many? 10,000 samples for beta and 10,000 samples for sigma square. Those using those samples for beta and sigma square, we can compute what? We can compute its mean and variance. Mean and variance of the 10,000 samples. Then these are mean and variance of posterior distribution of beta and sigma square given y. Okay, again, this is really important. In each step, in each iteration, we sample beta from what? Is beta from what? It's from full conditional distribution, or it's from its posterior distribution. Beta is sampled from its full conditional distribution, not from posterior distribution, right? Because if this term is not given, then this is beta's posterior distribution. But if sigma square is given, then this is full conditional distribution. So we sample beta and sigma squares from their full conditional distribution. Alternatively, but if we save the draws from the full conditional distributions, then theoretically it should be the draws from this posterior distribution. I'm not going to prove this. You can learn the proof in the graduate program though. Okay. So this is the gift sampling. Okay, and we are going to do this by MATLAB. Okay.